Hello everyone, welcome back to another lecture of COP-3402. Today we're going to be focusing on translating function definitions and function calls in simple IR into x86 64 AT&T syntax assembly. This is going to be the first of two lectures on this topic. So before we begin, let's just review what we're doing with this second half of the course. We are creating a compiler. We are writing a tool that will take some source language, in this case simple IR, and convert it to some target language, in our case x86 64 AT&T syntax assembly. The big idea is that we're not executing the code, we're not executing the simple IR code as we're flexing it and parsing it, we are instead just translating it to assembly code. If we were executing the simple IR code, then we'd be writing an interpreter, but we're not, we're writing a compiler. And the compiler must, crucially, it must generate assembly code whose behavior is equivalent to that of the original simple IR code. And so in this lecture, we are focusing on translating functions. So it might be useful to review what exactly is a function in a programming language. And there's many ways you could define this, but for our purposes, we're going to define a function as a named region of code with some inputs and outputs. Now, in some languages, you don't have to give your functions names, like in JavaScript or Python, you can pass anonymous functions that don't have names. And in some languages, functions don't have to have inputs, they don't have to have outputs. But in simple IR, every function needs to have a name. It may have some inputs, those are optional, and it has to have one output. So now let's draw a diagram to illustrate how the flow of control transfers between the caller of a function and the callee, or the function that is called. So we have here a diagram illustrating the function f. It's going to be the caller in this case, because f is going to execute some lines of code, that's what these three dots signify, and then call the function g. And then we're going to branch, because of the call to g, branch our flow of control to g's definition, execute some lines of code, and then return. And upon executing the return instruction here, control will flow back to the definition of f immediately after the call to g. And you can imagine that the execution will continue sometime past the definition of, or the call to g, I should say. And then eventually we would reach a return statement inside of f, and the flow of control would go back up to whatever called f, and so on and so forth until eventually we reach the main function. So in simple IR, the way function calls look is that we always have to have a variable that we are assigning a result to, and we are executing the call on the right-hand side here. So in this case, we have no arguments, so we're just saying call f to show a call to f. There's no parentheses involved, just call f. And then we're assigning the result to retval. And then we could assume some simple definition of f here where just f is defined to only return 5. Now, what exactly does this call instruction do? Well, it's a branch to the label f. So this assembly code here actually defines the function f. We have a named region of code, f, with this label, and it moves the value 5 into RAX and then returns. And this is actually the same as the definition we saw up here, because the convention in x86 64 assembly is to store return values in the RAX register, so we're doing that here. And then the ret instruction, well, among other things that we'll review shortly, return the flow of control back to the caller of f. And here we can see how f is actually called. We are calling f using the call instruction, and then moving the value in RAX into the -16 offset from RBP. So we can assume that the retval variable has an offset of -16 from the stack's base, the base of the stack frame, so the base pointer. And so this instruction actually moves the result of f out of RAX into -16 RBP. So it's important to note that in assembly, we don't just have like a way to get the result of a call to a function stored in a register immediately for us. We have to manually extract the result of that function call out of the RAX register and into the destination of that call. So in this case, -16 RBP. Now, what exactly are these call and ret instructions doing? Well, they're both doing two things. The call function is saving the return address first, so we'll see how that works shortly, what exactly we mean by saving the return address. And then it's branching, moving the flow of control to the definition of f. The ret instruction is just retrieving the return address, so that was saved by the call to f, and then branching back to that return address. So each of these these instructions, I should say, do two things. And you might want to know this for an exam. You might be asked, what are the two things that a call instruction does? What are the two things that a ret instruction does? So keep that in mind. Now to show an example of a call, let's go over to the whiteboard here. Okay, on my right-hand side, I have ScholarDraw open. On my left-hand side, I have the slides open. And we're going to step through these instructions one at a time. So we have the same instructions here on the right-hand side in the stack, or in this like stack-like structure here. This is really just the set of instructions in memory. So we're beginning at instruction number 3. And why is that? Well, it's because this is the first instruction underneath the start symbol. So recall that underscore start is the program entry point. The loader will look for this symbol when it goes to start your process, your program as a process in memory. So the instruction underneath the underscore start is going to be the first instruction that always gets executed. And in this case, that is 3. So we're starting at instruction 3. So what's going to happen here? Well, the first thing we do with a call to F is save the return address. And the instruction counter, so the instruction counter is going to begin at 3. Now, let me actually backpedal for a second. We have to begin with the instruction counter pointing at the first instruction of our code. Underneath start, the first instruction is 3, so we set the instruction pointer to 3. And this register RIP, perhaps creepily named, is going to be the register at which the instruction pointer lies. So you might remember from computer organization that the instruction pointer is the value that stores the current instruction to be executed in memory, the next instruction to be executed in memory. So if RIP is 3, that means the next instruction that needs to be executed on your CPU is instruction number 3. So RIP is going to start at 3. We're going to see this call instruction. The first thing a call instruction does is save the return address. Well, the return address is going to be the instruction immediately after the call. That's going to be number 4. So the saved address is going to be 4. And then we're going to branch to the function that we're calling. So we're calling F. So we're going to jump to the instruction that begins F. So underneath the definition of F, or the label F, the first instruction is 1. So we're going to go to instruction 1. So we're going to set RIP to 1. Now we're going to execute the code at instruction number 1. This says move. So we're going to move the value 5 into RAX. Then we're going to increment the instruction pointer because we just finished executing an instruction. Then we're going to execute the return instruction. So what return will do is first get the address and then jump to that address. So we're going to get the saved address 4, and then we're going to jump to that saved address. So I think this is what the slide said earlier, right? Yeah, retrieves a return address, then branches to it. So we're going to move RIP to 4. Then we're going to execute the instruction at 4, move REX into negative 16 RBP. So we're going to move the value in REX into negative 16 RBP, which is the place in memory where the retval variable is. So we're going to put 5 in retval. And then, of course, we increment the instruction counter by 1. And we don't know what comes next. It's not listed here in this code snippet, but there's presumably some code that comes after instruction 4. Now, this works. But as you might have inferred based off this note I have here in the slide, there's a problem with this example. And the problem is that we only have support for one function call. If we had multiple function calls, then this is not going to work because we would overwrite the saved return address each time, and we would be unable to return to the original function that had started our call stack. So instead what we do in practice is have a stack of return addresses. So maybe you've heard of the term Stack Overflow. This is when you have too many function calls and the data for each function call overflows the stack. And so you have a stack overflow. Let me zoom out a little bit more here so we can see all these register values. Okay, let me maybe zoom in a bit more. Okay, that's much better. I think that looks good. Okay, cool. All right. So with this example, what we're going to be doing is using a stack to keep track of the return addresses of our function calls. And what's important to note is that this stack is not like a separate stack in memory. It's the very same stack we've been using for storing our stack frames, our function calls frames in the stack. So this is the same part of memory. This is RAM. This is going to be virtualized, the same stack. But for this example, we're only going to be looking at return addresses. So to begin, we'll start at the first instruction. We're going to set RIP to instruction number 5 because that's the first instruction underneath the start symbol. So RIP shall be 5. If I can just select that there. Yep, there we go. Then we're going to execute this call to G. So what will this do? Well, it's going to push the value of G, or the return address of G, onto the stack. So the return address after this call to G is going to be instruction number 6. So we're going to take this value and push it onto the stack. So 6 should be pushed onto the stack because that's the return address after calling G at instruction 5. Then we're going to go to the definition of G, so line 3, or instruction 3, I should say, and by setting RIP to 3. Next, we're going to execute this instruction at 3, which is a call to H. So we're going to push a new value onto the stack. We're going to push the return address of the call to H, which is going to be 4 because 4 comes after 3. And now we're going to branch to the definition of H, which is what we're calling. So H is going to begin at instruction 1. Oh, and one thing I want to point out is that you might have noticed that we're pushing objects onto the stack downwards instead of on top. That's because in memory, and I've said this before, the stack grows downward. In x86-64 machines, the stack grows downwards. So when we push a value to the stack, it actually gets pushed one below. Okay, so we go to the definition of H. We're at instruction 1. We move the value 7 into RAX. So we're going to put 7 in here. Then we're going to execute, or actually we should increment the RIP register because we've executed an instruction. Then we're going to execute a return. So what we do first with a ret instruction, in practice what we actually do, is we pop the top value off the stack, so we get this value 4, and we move it into the RIP. So we put that there. And now we're executing from instruction 4. So we execute instruction 4. This is a return instruction. So we're going to, again, pop the top value off the stack. We're going to take the value 6, pop it off the stack, and put it into RIP. Now, we continue execution from instruction number 7. We're going to move the value in RAX into the location of memory where the retval variable is. So we're going to move the value 7 into retval. So I'll just do that now. We can copy that and then paste it and drag it over to retval. And then we would, of course, increment the RIP register by 1 again. But again, we don't know what comes after this. We don't know what instruction number 7 is, but we would, of course, have to increment the RIP register after executing each instruction. So that's the big idea. We can use a stack to keep track of multiple function calls, and each function gets its own stack frame for other purposes we'll see later. And one example of this would be function local variables. So we need to store variables for each function. We can't just use global variables for each function call. And to demonstrate why it would be a bad idea to just use global variables for storing all of our data, I have an example here of a potential implementation of a factorial function. So on the left-hand side here, let's assume we try to implement factorial, this function f, in C. So this int f function is factorial. And we use a global variable saved n for our recursive call, for storing our recursive results. Let's see what would happen if we tried to do this. First we would call main, which would then call f of 3, so factorial of 3, which I'm just going to write this down now. Factorial of 3 should be 3 factorial is equal to 3 times 2 times 1, which is equal to, of course, 6. So our goal is to get the result 6 from executing this function here. Let's see what happens. So we call main, we call f of 3. The first thing we do is check if n is less than or equal to 1. 3 is not. 3 is greater than 1. So we assign saved n to the value of n, which is going to be 3. So we say saved n is equal to 3. We then decrement n by 1 and say that f underscore n is equal to the call of f of n. So we're saying saved n is, or f of 2 basically, because n minus 1, n is 3, 3 minus 1 is 2, so we're calling f of 2. And storing the result in f underscore 2. And then we're returning the value of, down here, f of n times saved underscore n. But when we see this called f of n here, we're going to have to branch to the next recursive call. So f of 2, n minus 1, 3 minus 1 is 2, f of 2. We again assign saved n to n, which in this case is now 2, because 2 is greater than 1, so we're following this branch. And then we're calling f of 1, next recursive call. And in f of 1, 1 is actually less than or equal to 1, so we're going to return 1 immediately. That's what we do here. And now we're going to start bubbling back up through the call stack. So in the call to f of 2, we had said f of n was equal to f underscore n is equal to the result of f of n. That's going to be 1. Oops. And saved n was equal to whatever it was last assigned to, so 2. So we're going to return, ultimately, 2. And this is actually correct for f of 2. So factorial of 2 is in fact 2. So far, so good. Now let's go back up one more level of the call stack. So underneath the call f of 3, the f underscore n variable is going to be equal to 2, because that's the result of our recursive call, as we just determined. And then saved n is going to be equal to whatever was last assigned to n. So, or saved n. So we had last assigned 2 to saved n. So this is going to be 2. And the result is going to be 4. And this is wrong, right? Because we just said that factorial 3 should be 6, but we have 4 here. So clearly something needs to change. And what needs to change is that we need to use function local variables. So this is just an example of why we can't use global variables for everything. If we instead use locals for all these function calls, if we use saved n as a local variable, then suddenly this call stays the same, but the call to f of 3, we will use saved n as 3 here, 2 times 3 is 6, and now, oops, I pressed that button again, and now our function is correct. It works. 6 is correct. So this actually works, and it's because we use function local variables. So clearly there is a need for local variables for our functions to work correctly, or at least to make it easier to write correct functions. So how can we in assembly code allocate space for local variables? Well, the big idea is to actually just use the stack. So if we have a function here, example variables with 2 variables x and y, x equals 1, y equals x, return y, we can use the stack, the same stack that we're storing the return address, to store these variables. And we can use these push and pop operations to store them. So for example, we could push values onto the stack, and the way we would do this is by, for example, with push, subtracting from the stack pointer, which is going to be in the RSP register, and then copying data into the pointer address, and then using pop instructions to remove those variables, deallocate them afterward, which would copy data from the stack pointer address and then add to the stack pointer. So we're adding to decrement because remember the stack goes down. But in practice, it's actually faster just to avoid push and pop and just use a sub instruction for allocating space, because if what we're doing with push is subtracting from the stack pointer, it's faster just to subtract. We can just pre-compute how much space we need and subtract immediately from the stack pointer enough space for all the local variables. So what I want to show here maybe is an example of this. Let me see what the next slide is. Okay, I'll show this here then. What we could do is, let's say we have RSP, the stack pointer, the top of the stack frame, equal to 32. Then presumably some function has already called this function example variables. It might be some other function. It might be underscore start, the very first entry point of our program. So what we need to put in 32 is the return address, because presumably this function was called. Make this a little bit smaller. Here we go. And then to allocate space for our locals, we can just decrement RSP by 16. That's 8 times the size, the number of local variables we have. And the reason why we're multiplying by 8 is because each variable occupies 8 bytes in memory, because we're only dealing with 8-byte integers and simple IR. So we'll decrement RSP by 8 times 2, because we have 2 local variables, x and y. That's going to give us to 16. So now RSP is like right here. Now let me actually draw these local variables so we can see what spaces they occupy in memory. So x would occupy this region of memory, and y would occupy this region of memory. And the RSP would be here. Now, you might be wondering, well, Brent, this doesn't make sense. RSP is at the same address, begins at the same address where y begins at. Why is that? Well, the reason why this is okay is because, remember, RSP will only change again if we make a call to another function. And if we do make a call to a function, we would, of course, execute the push instruction first. So if we were going to have another instruction call, another function call, RSP would actually be incremented once, and then we would put the return address of the next function call here. So even though RSP is pointing to the same address as the last local variable, that's fine. We're not going to overwrite that local variable's contents with a call to another function. So we subtracted 16 from the RSP to allocate space for our locals. Then we can execute our code, whatever it is in the middle here, and then add 16 back to RSP. So we'll change this back to 32 to deallocate the space for these local variables. And we don't have to actually zero these out because we've just, there's no reason to zero them out. We just change the RSP back to the address of the return address. And now when we execute this return instruction here, what's at the RSP? Well, the return address. So we can actually go back to whatever function had originally called this example variables function. Now, we effectively are using the stack here as an array of local variables. So I mentioned before how we could use that RBP register, consider it like an array in C. And this is true because we're effectively using this array, this stack, as an array to access our local variables. Oops. And again, the reason why we use these offsets from the well, let me show you that next actually before I talk about that. So we are able to change RSP, but it would be nice if we had like a way to treat the base of the stack frame as our center from which we get our local variables as offsets from. And the way we do this, the convention for storing these local variables or accessing them, is to store the base of the stack frame in a variable, a register called RBP. And we typically do this by just moving RSP into RBP. So for example here, I'm going to go through this example again now. If we have a new register, RBP, what we would first do is move the value in RSP into RBP. So RBP here would be 32. Then we would subtract 16 from RSP. And now we can access all of our local variables as offsets from RBP. So to access X, for instance, we would write something like this. And the reason why this works for accessing X, let me actually draw this out here so we can see very clearly, is because if we take the value of memory that RBP stores, which is 32, and we subtract 8 from it, we get 24. And this is the offset at which the variable x begins. So x spans 8 bytes, and 24 is going to be the address at which x begins. And then, of course, when we're done executing our code here, we would add 16 back to RSP to go back to the address of the return address. And then we would execute this return instruction to actually read that return address and go back to whatever instruction was last executed or go back to the next instruction after the call to example variables. So recall that the symbol table is what we use to record the offsets from the RBP for all of our variables. And you might be wondering, okay, well, we used -8 just now. Let me undo this so you can actually see that again. We just used -8 for x. Why does this symbol table say -16 for x? Well, in practice, we have to push one more register onto the stack to follow the just requirements of implementing an x86-64 compliant, assembly syntax compliant compiler. We have to push another value onto the stack. We'll see it shortly. There's just something we have to do that we have to allocate extra space for. So in practice, your offsets are going to be all beginning at -16. So quick refresher on memory. Let's see. Yeah. So we could move a value into a register. For example, let me go down here. We can move a value 1 into RAX, for instance. I don't think I have an RAX register here. Let me see. Is there something else that I can use here as a good example? All right, so I'll just talk through these. So, of course, this move instruction will move an immediate value into RAX. We move the value 1 into the RAX register. This doesn't access memory because the registers are on the CPU. They're not part of RAM. They're not virtualized. They're just on the CPU. We could also move to a register value, so we can move the value in RAX into RBP. This would be a bad idea in practice because you don't want to change the value of RBP because then you lose the ability to access your local variables correctly because we always access local variables as offsets from RBP. We could also move the value in a register into a address held in a register. So in this case, we're getting the value in RAX, we're going to the address stored in RBP and moving the RAX into the value in memory that is stored in RBP. So for example here, if RAX had the value 8, we would go to the value memory address that RBP stores, 32, and we would put like 8 right here. Again, not a good idea in this case because you'd overwrite the return address. So we can also move to an offset from an address given by a register. So in this case, we would go to the value at RBP, then say, so 32, go to -16 below that, so that would be right here. So 32 minus 16 is 16, and then we'd store the value in RAX into that. So assuming RAX is the value again, like, I don't know, 8, then we could put the value 8 into the variable y this way. Now again, in practice, we're going to start with our offsets at -16, and we'll see shortly why that's the case. So now let's look at some assignments here. So a complete assignment from a constant, so x equals 1, becomes the assembly code. Move 1 into RAX into -16 RBP. Just some simple examples here. I think we've already seen a lot of this before in previous lectures, so I go over the lectures on assignment, on the introduction to simple IR to review these concepts. Okay, so now let's go over a more complex example with complete local variables. So again, what we're going to be doing here, let's actually step through these instructions on the left here, is we are making a call to this example variables function, storing the result in retval, and then in the callee example variables, we are declaring two local variables, x and y, saying x is equal to 1, y is equal to x, and returning y. So remember that in example variables, we first have to push or subtract from RBP to make space for locals, save the RBP pointer first to track the location of the locals in memory, and then access these variables via offsets from RBP. And we'll assume we use these offsets for x and y, and you'll see shortly that this isn't just something that I'm telling you. This is actually going to make sense shortly why this is the case. So the first thing we do is set the RSP to the top of the stack frame. So we're going to assume that this example variables function was already called by some other function. So I'm going to copy this. Oops. Copy this value, paste. I'm going to change this to return address. So we assume that the example variables function was called by some other function to begin with. And the return address is at address 64. And RSP is at that address, stores that address, 64. Then the first thing we do is move the RSP into RBP to store the base pointer. So we're going to replace RBP with 64. Then we have to do something new here. You haven't seen this yet. This is pushing RBX. So to follow the application binary interface of x86-64 assembly, which we have to follow to implement the assembly code correctly or compiler correctly, we have to follow the ABI. Application binary interface defines like the calling conventions of functions in a assembly syntax or an assembly flavor. So we just have to do this in order to follow the ABI. We have to push RBX onto the stack. The ABI dictates that RBX is always saved by the callee. So we're going to have to push RBX onto the stack. So if we say RBX has some value, I don't know, let's say 7. Then we're going to have to, of course, push 7 onto the stack. So what we would first do is decrement RSP by 8. So it'll be 64 minus 8 is going to be 56. Then we're going to put the value 7 at that address memory, 56. Then we're going to allocate space for our locals by subtracting 8 times the number of local variables we have. So again, example variables has two local variables, x and y. So we're going to subtract 8 times 2, 16. So RSP will be 40. Then we're going to begin our function body. So we're going to move 1 into RAX. And then move RAX into negative 16 RBP. So if we consider conceptually that we've just allocated space for x and y, x should be here, and y should be here. So we're going to take the value in RBP, 64, subtract 16 from it to go to 40. I'm sorry, 16 from it. So 64, subtract 16 from it to go to 48. And then move the value in RAX into this place in memory, which is where x is. So this seems to be correct. So we're going to drag the value RAX, which is 1. We're going to paste it in and put it right here. Next, we're going to assign the value y to x. So we're going to first move the value at negative 16 RBP to RAX. So RBP is 64, minus 16 is 48. What's at 48? The value of x, which is 1. Putting that into RAX, so it's already there, so I'm not going to change anything. Then we're going to move the value in RAX into the offset negative 24 from RBP. So 64 minus 24 is 40. So at address 40, we're going to put the value 1. Then we're going to return. So we're going to, or set up the return value. So we're going to move the value in y, because we're returning y. We're going to move the value at address of y, 1, into RAX. It's already there. Again, I'm not going to change anything. And now we clean up. So we have to deallocate the space for our local variables. So we add 8 times the number of local variables we have. So 16 to RSP. So 8 times 2 is 16. We're adding 16 to RSP. So RSP will be 56 now. Then we pop the value of our RBX. So we look at what's on top of the stack. RSP is at address 56. At address 56, we have 7, the original RBX value we had pushed. So we're going to put 7 back into RBX. We don't have to change anything in this case because RBX already stores 7. And then we decrement RSP by 8 because that's the next thing you do with pop. So first with pop, you get the value, and then you decrement. And then finally, we call the return instruction. And what this will do is take the value at the address that RSP points to. So RSP stores 64. We go to that memory address. We get the return address of that value. And then we branch to whatever address is stored here. So this could be main, this could be underscore start, this could be anything. We don't know. Okay, let me just check. All right, I think that is enough for today. Yeah. Okay, so we'll go over more in the next lecture. Right now, we've only set up enough for one function call because we're using move. We're not actually pushing the RBP onto the stack. So this may not work. I don't believe this schema will work for having nested function calls. So in the next lecture, we'll look at how we can set up the space for parameters and support multiple function calls by using a stack for storing RBP.